So picking up where we left off with thermodynamics, we started talking about the second law of thermodynamics, which says, for any spontaneous change, the entropy of the universe must increase. So we showed you this equation and we said we can change that variable, delta S of the surroundings, to really equal negative delta H of the reaction over T. But if we say delta S of the system, well, the systems that we're going to be talking about are all reactions. So we can change our equation to say it's the behavior of the reaction will determine whether the reaction is spontaneous or not. So in general, lower enthalpy and higher entropy for a reaction are driving forces. In general, exothermic reactions tend to be spontaneous, and in general, when delta S is positive, those reactions tend to be spontaneous. We're going to say it this way. Only two things in the world could make a chemical reaction occur. Either the reaction is dumping tons of heat into the surroundings because it's exothermic. Exothermic reactions cause the universe entropy to increase, or the products have greater entropy than the reactants, because a positive delta S of the reaction will cause the entropy of the universe to increase. So that's our two variables, entropy of the reaction and enthalpy of the reaction, because they are going to tell you whether the delta S of the universe will increase or not. So when our reaction is exothermic and delta S is positive, yep, always spontaneous. Turns out endothermic and delta S the reaction negative, never spontaneous. We'll talk about that some more. So it gets real confusing when we say delta S reaction, delta S surroundings, delta S of the universe, delta S of the system. All those little subscripts can get pretty convoluted pretty quickly. So there's a guy that came in to save the day to help us describe all this stuff in more simple terms, I think. So we're going to go through quick derivation. Bear with me, it's not too painful. If I take my second law reaction right there and multiply that reaction by negative T, multiply both sides by negative T, so I get delta S universe times negative T plus negative T times negative delta H reaction over T, that ends up just becoming delta H of the reaction, plus negative delta T, not delta, negative T times delta S of the reaction. Simplifying all that a little bit, sorry, we come up with one thing. The guy that said, well, let's simplify this mess is Josiah Gibbs. And so he said delta S universe times negative T, we're going to call that G. That's Gibbs free energy. That's the new state function that Josiah Gibbs talked about. So G is equal to delta H of the reaction plus negative T, let's just make that minus T delta S. Delta G is equal to negative, no, that's wrong. Delta G is equal to delta H minus T delta S. And all of those reactions, all of those subscripts are for the reaction. Yep. So if the second law of thermodynamics says delta S of the universe must be positive for a reaction to be spontaneous. If delta G is delta S universe times negative T, then a positive times a negative, delta G needs to be negative for a reaction to be spontaneous. The S of the universe must be positive for a reaction to be spontaneous, which means delta G must be negative for a reaction to be spontaneous. So negative G times the negative out front, we get a positive value. So if delta G is negative, the reaction is spontaneous. If delta G is positive, the reaction is non-spontaneous. You may also see it written that it's spontaneous in the reverse direction. If delta G equals 0, ideas, the reaction is said to be at equilibrium. So, yep, that's a good little disclaimer down there. So, all of that previous stuff was for constant temperature. Well, if we consider this equation, delta G equals delta H minus T delta S, those little zeros up front, those zeros up top mean standard. Delta G standard is equal to delta H standard minus T delta S standard. We'll talk more details about exactly what that means in the next lesson. But delta G equals H minus T delta S. That's an equation that's important that you must know. If I am given the reaction here below, this reaction, if we know that G is a state function, just like H is a state function and S is a state function, theoretically, we could calculate G the same way we might calculate H and S, as in the summation of the products multiplied by their coefficients minus the summation of the reactants multiplied by their coefficients. But it turns out that G is very temperature dependent. So if you look in the tables in the back of all the textbooks that ever existed, there are tables of values for G, for H, and for S. As it turns out, H and S are not very temperature dependent, but G is. Those tables in the back of the book are at 25 degrees Celsius, room temperature. So if you look up values for G in the back of the book and did products minus reactants, you would get an incorrect answer in this problem. But if you look up H and S in the back of the book and get a delta H of the reaction, this is delta H at 25 Celsius, really, because we use the back of the textbook to calculate that value. This is delta S from the back of the book at 25 Celsius, because we use the back of the book to calculate that value. However, we're being asked to calculate delta G at a different temperature. How is that okay? Like I said before, G is very temperature dependent, but as it turns out, H and S are not very temperature dependent. So, given this H and this S, we can simply plug it into our equation above. So, let's do it. If we say delta G equals delta H minus T delta S, we know that our reaction has a delta H of negative 1036.2 kilojoules. Our temperature is 492 Kelvin. It's important to know that that's in Kelvin. And S is negative 152 joules per Kelvin. Uh-oh, I have a problem, don't I? This delta H is in kilojoules. This S is in joules. It does not matter which you convert to what, but they must be in matching units, joules or kilojoules, in order to add together. So I'm going to put a little decimal right there and make my S into kilojoules. So now it's just a plug and chug, and I get delta G equals negative 1036.2 minus 492 times negative 0.152, and I get negative 961.22 kilojoules. If you'll notice, the S units are joules per Kelvin, but my Kelvin cancels out, and it must cancel out, so that I get kilojoules plus kilojoules, kilojoules minus kilojoules. Whatever. I get units of kilojoules in the end. So we would say that this reaction is spontaneous or non-spontaneous. Because that delta G is negative, this reaction is spontaneous. All right, back to it. So we got negative 961.22 kilojoules. So we said delta G needs to be negative in order for a reaction to be spontaneous. When is delta G actually negative? If we look at these examples, looking at this first one. When the reaction is exothermic and delta S of the reaction is positive, the entropy of the products is greater than the entropy of the reactants. When delta H is negative, delta S is positive, delta G is always and forever negative. Hopefully you can see if I put a negative here and a positive there, negative minus a positive, it's really negative plus another negative. That's going to give me a big negative value. That is always and forever positive. The other always condition is this one, a reaction that's endothermic and a delta S reaction that is becoming more ordered. The products are more ordered than the reactant. Positive plus another positive, positive minus a negative. Yeah, that's going to be always a positive value for delta G. That's no good. The two iffy conditions are when your reaction is exothermic, but your system is becoming more ordered. So if this term is negative and this term is negative, 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 this is, yeah, sorry. If this delta S is negative and this delta H is negative, yeah, it depends on temperature. If temperature is big, that makes this negative value very big. So that makes the reaction non-spontaneous. That gives you a positive delta G. If temperature is small, then this term becomes small. So your delta H term is dominant. If we look at our last one, when the reaction is endothermic, but it's creating more disorder, the products are more disordered than the reactants, it can be spontaneous at high temperatures. The reason is temperature times this positive value makes this term very large, and when this term is large enough, it makes the overall delta G negative. So that's an entropy-driven reaction. We'll talk next time about delta G quite a bit, so get familiar with it soon.